Is there audio now? Oh no. Yeah, is there audio now? Yes, there is. Okay, good. So let me. All right. Oh, one more thing. So the TAs asked me to say this. You guys are going to be scientists, so you got to learn or get used to the following method. If you are writing in your homework or any text, if you're using an identity, you must cite it. Either you prove it or you cite it. It was discussed in class, you write discussed in class. It's in the textbook, you write discussed in the textbook somewhere, right? You're not allowed to use an identity that you have not proven or not cited. That's just the way science works. Okay? But there were a bunch of complaints about that by the TAs that like someone used an identity and just like, all right, if you know this identity, that's the answer. Right? Kind of thing. So whatever you're not citing, you should derive. Good. So let's do a quick review of the last lecture. The last lecture, we started by talking about the following function called Shannon entropy. Oh, sorry, I just interrupted myself. So yeah, we're gonna have a discussion of a statistical mechanics of identical particles because it's absolutely essential. And I'm not sure how much I can do about it. You haven't seen your undergrad, so I'm going to cover it. But then we'll be a little bit behind the discussion of symmetry, which is, I guess, okay. All right, so this is the function. It's a function that takes as an input the density matrix and comes out a positive real number. All right, its properties we listed. It's non-negative. Is equal to 0 if and only if psi is pure, which is the case if and only if there exists a ket psi such that sigma is this. All right. At this size of, I'm going to fill up the board a million times. In d-dimensional Hilbert space, complex Hilbert space, f sigma, well, actually, is less than equal to log d with equality if and only if sigma is 1 over d identity, so-called maximally mixed state. All right. We also said another thing, which is for a pure bipartite, my handwriting is not legible, let me know. State psi AB, the reduced density matrix that reduces to sigma A and sigma B, S of sigma A is equal to S of sigma B. Do you recall how we proved this? Or how do you derive this? Just wait to see this. Schmidt decomposition. So we said every pure pseudo bipartite system will admit the following decomposition. There is square root. I don't remember if I wrote it as square root or not. With a basis, an orthonormal or orthogonal basis, basis for A and B, and it's pretty straightforward to calculate sigma A and sigma B from this and see that these lambda, actually this is square root, or even P. These are the eigenvalues of the density matrix. Therefore, that's what you would be working with. This becomes the Shannon entropy for those PIs for both A and B. Any questions? All right. Any questions about entropy? Then we talked about identical particles. We said that in quantum mechanics, there is no meaningful way, if you're talking about particles, there's no meaningful way of saying this particle versus that particle unless you have an observable that can distinguish them. So you need, in classical physics, labels and tags are free. Labeling things is free. You just put this is particle A, you know that, doesn't matter. This is particle B, you know that, and that's just part of your description. In quantum mechanics, there must always exist an observable associated with these, and when you don't have access to that observable, we talked about the symmetrization postulate. We said that if you don't have access to that observable, the particles must be treated identical, right? So that was the principle. Then we said that okay, good. When you're treating them identical, it means that there's no way for you to distinguish between. Let me see how they were right. Let's say you have a two-particle state that looks like this, right? There's no way for you to distinguish between this or this or any superposition of them, right? All right, so that sounds confusing. What are we going to do? Here comes a postulate of symmetrization of quantum mechanics. Postulate of symmetrization says in dimensions 3 and above, spatial dimensions, 3 and above, there are only two types of particles, identical particles, bosons and fermions. When you're dealing with bosons, you always totally symmetrize. And when you're dealing with fermions, you always totally anti-symmetrize, right? So is that semi-clear, or do I need to write it down? Good? All right. Any questions about this? And then we talked about two dimensions, how the story is different. Frank Wilczek, we talked about how Frank is going to be here giving a talk tomorrow, I believe. And now you could actually go see him. Any questions? We talked about actually the swap operator as well, but I'm not going to repeat that because we have a lot to cover today. There was another thing that we talked about. That was I presented that some of them are serious. Oh, it's at the end of the board. Connection that is an empirical observation at the level of quantum mechanics. But what was it? Do you remember? It said that there was a connection between spin and statistics. So statistics here, for now, I said we mean boson versus fermion. But today I'll explain what is meant by why do I call this, or why do people call this statistics. What was the connection? So we said that there are two types of statistics, bosonic statistics and fermionic statistics. What is the rule? Spin of boson is always integer, and the spin of fermions is always half integer. I'm not going to write it. Good? Oh, sorry, I forgot to mention this. So I think, well, it's pretty clear that the fact that you have to anti-symmetrize fermions results in the so-called Pauli exclusion principle, right? You cannot put two fermions in the same state because the fact that you have to anti-symmetrize them, you cannot put any pair of fermions in the same state because anti-symmetrization will tell you that there exists no such wave function, right? So coming back here, this was the relation that we said, and I did not explain why. Do you want me to do a very quick and dirty argument? I'm gonna use analogies or proof. Okay? So this is not a proof in any way. Imagine you have, I'm going to draw this two-dimensional. Imagine this is a slice of space, and I have two fermions. So what I'm going to give you is a definition of a fermion that we have not seen, and it is a fundamental definition that from which all of these results follow. So here's fermion 1, fermion 2. All right. What is the wave function we're dealing with? We're dealing with, I don't know, for example, this is, let me put the center of the coordinates in the middle. So this is psi of minus r. Psi 1 of minus r, this is psi 2 r. Right? Okay. What is the statement? The statement is that if you switch, this is equal to minus psi 2 of minus r, psi 1 of r. What is the physical operation that switches the two? As an experimentalist, how do you realize swap? Rotation. It would be rotation by angle pi around the center, right? You will take this and rotate it this way. So it's rotation around the center, right? So here's a definition, if you wish. Or maybe say it a little bit differently. If a fermion, so these are wave functions for now, but for a second forget about quantum mechanics. If fermion is a particle with the following property that as you rotate it around, come back, rotate it by 2 pi and come back, you don't come back where you started, you pick up a minus, sign, then we can explain this. Why? Because I take this fermion, I go around by angle pi, that will give me a factor pi. I have 2 of them, I'll take a minus. Bosons are objects that as you go around by 2 pi, they come back where they are, so we end up with a plus. This is the field theory description of it. These are wave functions. I understand that, but in quantum field theory, wave function is an operator. Blah blah blah. Anyway, so that was what I wanted to mention. I wanted to say that the fundamental thing that makes a boson boson or a fermion is the fact that if you take a boson and rotate it in space by 2 pi, it comes back like what you started. But if you take a fermion and go around, you end up with a minus sign. Now, a challenge for you. What does it mean that you go around and come back and pick up a minus sign? Is that observable? No, because in physics, you rotate by 2 pi, things come back, right? How could you observe that minus sign? Just for you to think about interference. That's the way you would observe it. It's a purely quantum phenomenon. Anyway, we teach this in quantum field theory. So this is not quite true, because if you really wanted to prove this statement of this stuff, you have to use causality. That's a little bit more involved, but this is like quick and dirty argument. Any questions about that? So fermions are things that as you go around by 2 pi, they don't come backward. They pick up a minus sign. Fermion is not an observable. What is an observable? 2 fermions, a pair of them. All right, enough quantum field theory nonsense. Okay, so this is what I wanted to say about the last section. Now we're going to start that discussion on today's section. Yeah.
When we go to the fermion it sounds like pseudo-vector has.
No. Okay, go ahead.
And pseudo-vector must have duality with regular vector. Is it connected to?
No, sorry. If you're talking representation theory, it's a projective spinor representation. Projective representation, that's mod C2. Pseudo vectors and that's not quite the terminology used here. So put that aside. It's just an object that you go around by 2 pi, doesn't come back where you start, picks up a minus sign. And it can only pick a minus sign. We'll explain that too in 3 dimensions above. That's how we prove it. All right, I'm not going to talk. That has to do with the topology of the Lorentz group, blah, blah, blah. Yeah, so if you want to know what this object is, it's called a spinor and a spin half. This is literally what I said. Go around by 2 pi, you pick a minus sign. All right. So today we're going to talk about quantum statistical mechanics. But that might sound fancy. What we're going to talk about is basically consequences of the symmetrization principle when you're dealing with lots and lots of particles. Right? Real world physics is most often statistical physics, right? Because you have like an Avogadro number of particles, and now that the fact that they're indistinguishable in quantum mechanics will have dramatic consequences that we're gonna discuss today. Good. All right. What is how intuitive is entropy to you guys? How intuitive is like core squaring? Do you want me to briefly go over it, or do you want me to? Either or. Want me to go over it? All right, let's go over it very quickly. So, what's the situation in classical physics? Imagine you have a system with many little magnets. These could be atoms, like an Avogadro number of atoms, and each of them, they might have like some sort of a, they might have a little vector pointing in some direction, angular momentum, or whatever, right? Or they could be up and down, right? They could be just up, down, like the hard drive, right? So let's actually simplify it and say they're up, down. So if I have n particles, this is classical physics, and each of them will have two possibilities. We call them, let's use the word classical degeneracy. Common word degeneracy for this as well, right? Let's say they have the same energy, up or down have the same energy. How many configurations do I have? 2 to the n, right? Each configuration, we're going to call it a microstate. That's hopefully clear. For the rest of your career, that's what a microstate should be, right? How do you observe a microstate? How do you decide what microstate it is? You have to perform an enormous number of measurements. But that's unrealistic. If I have an Avogadro number of atoms, I can never do such a thing. What I can always measure at best is a couple of observables. So I'm going to measure a couple of observables. For example, in this example, a couple of one particular observable would be, if these are little magnets SIs, would be the total sum. Wow. All right, this part of the chalkboard is dead. The total sum. Let's say I have a measurement device that's supposed to measure like the amount of magnetic field here, right? But my measurement device is like large compared to the size of atoms. So what it actually measures is the total sum of magnets here, right? So that's what they observe. Now, let's say I have a slab with n atoms, and I measure the total sum, and I get like, it's chalky so man. I read that the total sum is 2. What does that mean? What does that mean in terms of my microstate? So it means that any state, any microstate that has 2 extra ups compared to downs could have been what I measured. Right? Yeah.
How do you do these measurements if the spins are correlated?
Oh, let's start simple. Okay. All right. So then what is my state? I don't have a complete description of it. That is what a macro state is. And this is what a macro observable is. Microstate, macrostate. A microstate is a single state. A macrostate is an ensemble of states, right? Because you have no idea which is your state. It could be all down and then the last 2 up, or it could be the first 2 up, the rest down, or it could be any other configuration that has like 2 extra ones, right? So you have an ensemble, a collection of such states, right? This is the origin of ensembles in classical mechanics. Good. And you hopefully see the notion of degeneracy, right? Probabilities come in because you just have access to macro observables, or your observables are coarse-grained. You have no choice but associate to a macro state some probability distribution. What is the principle? The principle is the following. All distinct microstates compatible with your measurements are equally likely. This has a name. Anyone? What's it called? It's a principle in classical physics and quantum mechanics we derived it. Yes, equipartition. Yeah. It's a principle in classical mechanics that we're not in this course, but it's something we understand quantum mechanics, right? Equipartition says that all distinct allowed microstates that are consistent with your macro observables are equally likely. So what is the probability distribution ensemble you associate your macro state? You take, let me make this simple. Let's just say n is let's say n is 3, and you observe that the total sum is 1, right? So it means that you have this state is allowed, this state is allowed. Oh, yeah, no, that's good. And this state is allowed. These are the only allowed states, right? So what is your ensemble? What is your macro state? Probability third here, probability third here, probability third here. Good. This is equipartition. I'm not gonna write this on the board, but this with this crappy chalk. Good. All right. What is entropy? Can anyone give me a definition of entropy? Exactly. So here, consider this setup, but the macro observables I can see is energy, right? So I have a lot of atoms, and all I can measure is energy. The total energy could be made in different microstates, right? There might be many different microstates that are consistent with the same energy that we have. So equipartition says that every energy microstate is equally likely. Energy microstates with the constraint that the total energy is equally likely. I lost the train of my thought. And then entropy, and the number of such microstates that can, I can write it here, right? Yeah. So let's say your total energy is E, and this is the sum of E1 plus E2 plus all the way to En, right? And each of these guys, you might have a couple of different ways of realizing this, right? So any such configuration of energy distributions is a microstate that's equally likely, right? We say a micro canonical ensemble is an ensemble where you have measured only the energy. That's what a microcanonical ensemble is, right? So let's say the number of states that contribute to energy E, the number of microstates, distinct microstates that contribute to energy E is omega of E. Good? Everybody's with me? What is entropy? Entropy, the master definition of entropy is this, minus log omega. By the way, this is from the previous lecture, you could tell this is von Neumann entropy. But if you can see it, good for you. This is nothing but von Neumann entropy. All right. Is this idea clear? It's very fundamental. So ask questions, because as we go to quantum world, it might get it gets a messier a little bit. This is all classical physics, right? So when I was saying that in quantum mechanics, you don't need ensembles, you don't need probability, coarse graining or macro observables to deal with probability distributions. Now, hopefully you see what I was talking about. Good? All right. So what's the situation in quantum mechanics? In quantum mechanics, imagine again you have n particles. Let's say they're free, so the question regarding interaction, so let's not make things messy. Again, you write the exact same thing. You have a Hamiltonian and it's a free Hamiltonian, it comes from H1 gas.
Sorry, really, why is there a minus sign there? Because I thought, that's positive. It's P of I, and that's less than one, but number of microstates is greater.
Sorry, why is there positive there? No, there's no minus sign, sorry. Yeah. That doesn't- By the way, from here, can anyone guess what temperature is? This is the very definition of temperature. 1/T is del EST. That's original. There's no other definition of temperature. All of them are up. All right. Here, back to this. So we have a Hamiltonian, which is some bunch of individual terms, right? And each of them will have the associated sum energy E to them, right? And then they could have degenerate, single particle degeneracies, like that. Is that exactly what I mean? For example, if my Hamiltonian was, if these are spins, and my Hamiltonian H1, the term on one, is SC squared, I have a twofold degeneracy for this side, up and down at the same energy. That's super boring setup, right? Because then all states have the same energy. But there could be degeneracies. Good. All right. So this is energy, total energy. What you're going to end up with is a bunch of these lines. They're all going to be integer space. So these are integers, right? Because you can see I'm summing a bunch of integers. The outcome is going to be integers. But the degeneracies, the omega of E is the number of ways you could partition an integer n into, an integer E into n pieces, right? So this is partitions of integers. Good. I'm gonna go through this in equations, but I just want to first set it up. If I have number 3, there are various ways to partition it. Do 3 partitions of 3, or 2 partitions of 3. 1 and 2 and 2 and 1, and 0 and 3 and 3 and 0. Those are the partitions of 3 that are allowed for two bipartite partitions. All right. So as before, the principle in quantum mechanics is going to be the same for the whole of this course. The assumption is going to be quantum equipartition. All microstates are equally light. Correct. Where this comes from is, for now, it's a principle, but anyway. The temperature is, oh, sorry, maybe the temperature has a minus sign. No, it doesn't, sorry. The temperature, by the way, this is called beta. 1/temperature is called beta. What unit does it have? Well, depends on your units of H bar. This is a length in physics. But, okay. Maybe that was a little bit of an advanced comment, but good. All right, so what we're gonna do in the 45 minutes that we have left is the following. First, I'm gonna give you an example of a bunch of particle configure a setup like this, and I'm gonna do explicit calculations of different microstates and how, whether there are 3 options. Distinguishable particle will give me one situation. Fermions, indistinguishable particle fermion will give me another situation, and indistinguishable boson will give me another situation. First, I'll do it through an example. Then I'll do it maybe on my iPad because it's lots of long equations. But first, I just want to work out an explicit example. And then the goal is to see how the expectation, the idea of equilibrium and states will change dramatically as you go from distinguishable particles to indistinguishable particles. It's dramatically different. Unfortunately, I don't think we will have time to. How many of you guys know what a Dirac-Fermi distribution or Bose-Einstein distribution is? All right, so at least some of you have seen it. We almost arrive it, but we'll stop at the end because we will run out of time. We're almost there actually by the end of this lecture. All right, so what's the setup I'm considering? The setup I'm considering is that each particle is not a spin, but I'm just going to write it here. Each particle is found as a quantum particle that is exposed to the following potential that has width A. It's an infinite potential well. We did not solve this problem, but I imagine you've seen it in your quantum mechanics courses, right? So what are the wave functions that are allowed? Well, these are the eigenstates of this infinite potential well. Let me just draw two because I can do better. The energies are going to be like this. They're going to be, so the eigenvalues are labeled by positive integer n, a natural number. And the energies are going to be pi squared h bar squared over 2m a squared n a squared. Sorry, there's no a, n squared, right? This is just an infinite well potential. Let's just make sure everybody is paid on this. So every single particle that I have is one of these quantum particles, right? Infinite potential well. Good. Here, a microstate of a single particle has no degeneracies. When I say what n is, I've told you what the state is and uniquely decided the energy. There's no way of having two energies for the same particle. But we're gonna, as we go to the next example, we're gonna build up on that. Okay, that's good. All right. So here's the setup. I have three such particles. All right. So what's my total energy? I'm going to call them A, B, and C. Of course, these are classical labels. So we'll see in a bit what's going to happen. So the energy is going to be EA plus EB plus EC because they're free. They're non-interactive. Good. All right. So I'm going to write down this equation one last time and then drop this term. So this is what the energy is. From now on, I'm going to measure energy in these units. So I'm just going to talk about the integers, positive integers. Good. Now I'm an experimentalist. I have access to total Hamiltonian energy. And I observe it, the state collapses into a microstate of energy. What was my example? 363. So total E is 363 pi squared h bar squared over 2m squared. I said that's my last one, but I'll write it one more time. Right? So this is the amount I've observed. But nobody complained. This is not a collapse of a wave function. There's not a single state that has this energy. There are many states. This is a macro observable. Right? When I observe this, any micro state consistent with this, as we're going to discuss, is allowed. So this is my macro observable. Hopefully you can read my threes. Sometimes I cannot read my threes. All right, so what are the microstates? I don't expect you to do it in your head because I cannot do it in my head either. So here are the microstates. 11, 11, 11. The first particle is that has Na11. 11 squared is 121. It's three of them 363. So I copied from the book properly. All right, so this is one microstate. This is another microstate, 13, 13, 5. But then there's also 13, 5, 13. And then there is 5, 13, 13. Good? I have 1, 1, 19, 1, 19, 1, and 19, 1, 1. I have 5, 7, 17, 7, 5, 17, 7, 7, 17, 5, 7, 5, 17, and two more that I want to write right next to this. 17, 5, 7, 17, 7, 5. Right? So there are a total of, if I can count, 13 microstates. All right. If the states are distinguished, if the particles are distinguishable, what is my ensemble? Remember, the rule of equipartition says every allowed microstate is equally likely. So what is my state? No, it's equipartition just says probabilities. We're not superposing at all. It says equipartition says you have this pure state with probability 1 over 13, because there are 13 total of them. So it's going to be a mixed density matrix. This microstate is the same in quantum mechanics and classical mechanics. This microstate with probability 1 over 13, this one 1 over 13, this one 1 over 13, and so on.
Even though it's the sort of quantum equipartition thing going on, it is, we are classically mixing the probabilities
Yes.
without
Absolutely.
collapsing the wave function.
There's no, it's not about collapsing the wave function. What you want is you have measured some energy. You want to associate state, which is in general a density matrix to this. And the principle is, as a physicist, you should be associating this density matrix. Now, if I was teaching quantum information theory, I would derive that for you. But it's if you wish, it's the minimum knowledge or maximum entropy principle. But I have not explained that. All right, so but that's the rule. For this course, it's the rule, right? So that's what the state is. Do you know how to write the state? So it would be 1, 1, 1, get 1, 11, 11, 11, 1 over 13, 1 over 13. I don't know. For example, this guy 7, 17, 5, 7, 5 plus 10. Right? Good. Another way to write it is this: 1 over omega e sum over E1 to E3, E2 plus E3 equal E1, E2, E3, E1, E2. It's equivalent. Right? This is called a microcanonical ensemble. Fixed energy. Good. So that's the setup for distinguishable particles. What if the particles are indistinguishable? For example, yeah, what if the particles are indistinguishable? What happens here in this counting? It's 1 per row. Very good. It's 1 per row. Yeah.
I still don't understand why are we considering superpositions? Those are valid states.
Okay, superposition with coefficients C1 and C2. Give me those coefficients. What is the rule that's going to decide those coefficients? No, any C squared, C1 squared plus C2 squared equal to 1. For any C1 and C2 would work. Which one are you going to pick? I'm telling you that this is the principle to pick it. It's a little bit like the symmetrization principle. you can't distinguish between any superpositions or either of the orders, but then the physics tells you this is what you do, symmetrize or anti-symmetrize. This is also, if you wish, a principle, but I don't want to call these principles because like at some point we're going to derive them, not in this course, but it's something that follows from basics. Yeah.
I'm still not quite sure, and maybe this is a subtlety I missed way earlier in the course, how we get like mixed states with these classically behaving probabilities without having an ensemble of these three.
You're brainwashed by quantum mechanics. So probability distributions and getting mixed state is just like the way we always have been getting them, right? That's how we always got. What is surprising is that in quantum mechanics, sometimes you get these ensembles without coarse grain. Look, in quantum mechanics, you could still coarse grain, and that's what we do because it's relevant, right? If I still have like the hard drive on your computer is an insane number. Actually, a single up and down ferromagnet in your hard drive is not a single atom. It's like a whole bunch of atoms, right? So it is relevant for physics still. And mixed density matrices are equal good choices. Now, I understand I haven't explained why this choice, but it's called principle of equipartition for a reason. Good? No?
So we do have many copies of this. So.
We have many copies of this. No, take a little bit of a different attitude, approach. Quantum mechanics tells you have a system, you do measurements, and based on your measurements, you associate states with the system. What you read will tell you what to associate with the system. That's actually called tomography, quantum mechanics. So if you did only one measurement in this setup, the state that you're going to associate with this. Good. Microstate doesn't exist before, independent of your measurement, in a sense. We associate states with things. But okay, so we'll come back to this.
It's like a shot.
Let's not make it complicated. It's a lot simpler than that. That is a very relevant thing in real world. This is so idealized that those complications don't even come up. Good. So for the rule is that equipartition is a principle. If you only measured energy, all microstates are equally likely, and you must be describing your state as an equal, as a classical mixture of these states. Good. Take it to the principle. Because we have finite time. I'm happy to tell you more about it, but it just typically we don't teach information theory enough so that I can give you a one-liner. I did give you a one-liner. It's a minimum information principle, minimum knowledge principle, but it's not even a principle. It's saddle point of approximation. But all right, what was I gonna say? Yeah, what changes when the states are when the particles are distinguishable? This is one allowed state. This is also one allowed state. You cannot distinguish between them. So this is one allowed state, this is one allowed state. Only 4 allowed configurations. How does the situation change for bosons and fermions? Bosons say that, well, you got to symmetrize this, right? Doesn't really need it. You got to symmetrize this, this, and this. So symmetrization principle associates one totally symmetric state for bosons to each of them. How about fermions? What happens with fermions?
Two particles in the same state.
This is not allowed. This is not a microstate. This is not a microstate. This is not a microstate. There's only a single microstate for fermions. That's it. Because these guys, Pauli exclusion principle forbids them. So you already see how dramatically they. So what happens if you were dealing with distinguishable particles? You would get a mixed density matrix with 13 equal possibilities. When you were dealing with a boson, you would get a density matrix with probability 1/4 for each of these few states. If you're dealing with a fermionic system, you will get a pure state, which is a mixture of these. Totally anti-symmetric state. Good. So it's pretty clear that the entropy or the number, this omega of E is, well, entropy is just log of omega. dramatically different. Good. Now that I've made this one, it's important that you ask questions now because the next step is going to be, it's going to get a little bit ugly, like calculation wise. And you will have to track it later in your notes. But this is the principle. Is that clear? So one last subtlety that I want to mention, because it will come up in the next example, is how would the situation change if individual particles had degeneracies? So for example, if this individual particle has a degeneracy 2, right? For distinguishable particles, it will be just everything will be multiplied by the number of possibilities will multiply by 8, right? So you would have 1 over 8 times 13 for any such microstate, right? What bosons and fermions, like what it gets messy. We're going to do that. The counting is a little bit non-trivial. Good. Now, staring at these equations, can you see? By the way, this is already on the way to field theory. It's pretty darn close to field theory at this point already. Can you already see an organizing principle for writing these states? For say bosons, pick bosons. Writing all of this is stupid if I'm just gonna finally know that I'm gonna symmetrize or anti-symmetrize. So what information should I keep track of? Let me make a suggestion. So do not confuse little n with capital N. I apologize for the notation. So all that matters from this state is that state N11 is 3. It means that I have 3 particles of energy 11 and no particles of any other energy. This I can intelligently represent as N5 is 1, N13 is 2. All I keep track of is the number of particles of a particular state. Why? Because the particles are indistinguishable. It doesn't matter who has what. As long as I know how many of them have energy 13, I'm good. This would be N1 is equal to N19 is 1, and N17 equal to N5 equal to N7 1. Good? So how am I going to describe these? I wish I had called it chart. The way I'm going to describe these is just in your head. Think of an infinite vector. The first element of it is how many states how many particles of state energy 1 you have? State 1 you have. You have 0. How many particles of energy 2 you have? 0. You go until you reach the 11th guy, you put a 3 and then 0, 0, 0. Good. That's what this means. Similarly here, you're going to have 0, 0. Then you reach the 5th element. You put the 1. Then you go all the way to, oh sorry, I had 2 left. 3, third element. And then 1 and so on. Right? When you construct these, okay, that's what it is. Everybody's with me? So we're just going to keep track of the total number of excitations of the total number of particles of each energy. Good. How would things change for fermions? For fermions, the way we'll change is that when you look at this vector, all the numbers must be either 0 or 1. Right? That's it. That's the only solution. So let's say, okay, I said all of this. Let me say one more thing. There's another probability that you could ask. It's a more practical question. Let's say you have a fermionic state of these 2 particles. The particles are fermions. You could ask the following question. What is the probability of picking a fermion and it having energy 7? What's that probability? Third. Right? Let's say the system is bosonic. What's the probability of picking a boson that's it. And getting 5. One over 4, because these are equal likely. Then you have one single state here times 1 over 3. Right? You have 4 states equally likely. It's only this state that has particle of energy 5, and then there are 3 particles with probability 1. Sorry. Oh, sorry, I picked it back. 7. All right. Let's not make that less common. All right. What if the particles are distinguishable? It becomes 1 over 13 times 1 over 3. Right? So now you see how dramatic this is, right? This is a tiny, tiny number. This is a large number. This is somewhere in the middle. You have a fermionic system, bosonic system, and like a distinguishable particle system. You had the total amount of energy that was the same. You pick particles, and the probability of picking a particle that had an allowed energy was dramatically different. Yeah.
Why would it be 113 instead of 613?
613.
There's 6 states that include.
Oh, it's 613. Sorry. Yeah. Thank you. 613. They all have it. So it actually ends up being for distinguishable particles, yeah, there are 613. Yeah, correct. So it's 1 over 26. Thank you. No, 2 over 2. So 2 over 13. 2 over 13. So they're very different. That's the point. Now, do you guys remember the what's it called? Maxwell-Boltzmann distribution? What is it? You have an oven, and it throws particles at you, and you measure its energy. And you were supposed to plot the energy distribution, the number of particles of certain energy you get. That's like a probability of getting a particle of certain energy. Now you see, if that inside that oven, the particles were distinguishable, there is a different distribution you get. It's called Maxwell-Boltzmann. If they are bosons, you get the bosonic distribution, Bose-Einstein. If it's fermionic, you have the Dirac-Fermi distribution. We're not gonna exactly derive it. I'm almost gonna derive it because we're running out of time. But I just want you to know how to finish the argument, right? Good. Are there any questions about this? The next step is the general case. I'm just gonna do this analysis in full generality for bosons, fermions, and distinguishable particles. And then you will see almost see the Dirac-Fermi and those distributions. Any questions? Okay, how many of you guys know what Stirling approximation is? I'll give you a homework problem, but you absolutely have to learn this. It's pretty straightforward. I'll write the approximation, but I won't have time to prove it or write it for you. It's something that every physicist must know. Actually, I would say every scientist must know. But that's me being arrogant. All right, general case. So again, you have a total energy E. When I say general case, I still mean non-interacting particles, right? Interactions make things messy. E2 plus da 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 to En. So I have N. No, I don't want to call this. Oh, who cares? Just more. Lots of particles. I don't need to keep track of them. And there are D1. These are microstate degeneracies for single particles, right? D2 and so on. Actually, do I want to? Yeah, no, this. Sorry. I said poorly. That's actually okay. Yeah, D1, D2. That's okay. All right. So the question is this. Given a total energy E, what is Q of N1, N2, da, da, da? It means what are the total number of microstates Yeah, what's the total number of microstates with N1 particles in energy, N1 particles of energy E1, N2 particles of energy E2, and so on and so forth, right? We just said that that's the way we want to describe it. We want to talk about how many particles of certain energy we have. So this is the number of microstates with Na particles of energy and in EA. Good. This is such a terrible chalk. I don't know how it's possible to make such a bad thing. All right. Distinguishable particles. How do we want to? Okay, so we're gonna do how much time do I have? I'm gonna do this very quickly, but it's in the notes, so you can read it. So let's do distinguishable. How do we calculate this? There are N1 particles. Let's say the total number of particles is N actually. N is the total number of particles. I think I need it. So how many configurations do I have? How many ways can we select N1 particles out of N to put them on the first state? Is N choose N1, right? Do I need to explain this? This is the binomial distribution. Is this clear where it comes from? Yeah. Energy level. Oh, sorry. Yes, I use capital A and B and C for parts. Right? These are energy level. I'm now going forward. I'm talking about those vectors, right? Number of excitations of a certain time. Good question. Is this clear, or do I need to explain it? Let me just say quickly. So N choose N1 means, well, you have to choose N1 things out of N. The first one you have N options for, right? Yeah, N1, sorry. Wait a second. Let me not do the binomial distribution. I'm kind of confused why I. Yeah, okay. There's N1 way of picking the first one. Then there's N1 minus 1 way of picking the second one, and so on and so forth. And then at the end, it doesn't matter whether you pick the 31st one first or the last. As long as it's in this bin, it's the same. That's why you divide it by this. It's binomial distribution. It's easy to get yourself confused. All right, but now you have N1 particles in this. Each of them has D1 degeneracy possibilities. So you have to multiply it by D1 to the power of N1. I think I said it wrong. If I'm choosing N1 out of N, the first one has N possible, then N minus 1, N minus 2, all the way to N minus N1. And then there are N1 permutations that you have to divide by. But anyway, the final. Is this sensible? All right. So what is the total Q? Q of N1, N2, is oh, actually, sorry. How does the situation change for the second one? Yep. It's N2, but also you have already selected N1 minus 1 out. So it will be N minus N1, because you already allocated N minus 1 out, and then N2. Right? Okay, so this guy is going to look like N1 factorial, D1 to the power of N1, N minus N1 factorial, N1 factorial. My handwriting is bad. This chalk is bad, and there are lots of indices. I apologize. N2 factorial. Oh, yeah, N2 factorial. d2 to the power of n2. Uh, n minus n1 minus n2 factorial, n2 factorial, so on and so forth. Okay? What is this? It's, you will derive this, but it's n factorial, n to the power of infinity, dn nn over nn factorial. It's in the notes, so if you cannot read it, you will check it. All right, good. All right, so this is the setup, the counting for distinguishable particles. I have 7 minutes to do this for bosons and fermions. Let's do the fermions. Fermions is very easy. All right. There's only one n particle state with a specific set of there's only one n particle state in which a specific set of one particle states are occupied. Good. All right. So what is the situation? The only number that we're gonna get that's not one is out of degeneracies. Let's first establish that. We saw that in the previous example, right? When we talked about fermions, you only had one microstate and you anti-symmetrize that, right? So it only comes from degeneracies. So you have dn degeneracies, and you're gonna put nn fermions in that. And that's it. So for fermions, if you don't have degeneracies, the counting is just one. This is infinity dn factorial nn factorial dn minus. Good. All right, bosons requires a little bit of attention. All right, is this good? Is this okay? All right, for bosons, let me just focus on this part, right? So I'm gonna come up with this. Let's say Dn is 5, so, and then Nn is 7. There are 7 bosons, and I have a 5-fold degenerate state. Good. Why was the counting easy in the case of fermions? Because you could only assign a single fermion to a state. Here, there could be multiple bosons in a single state. So even though the degeneracy is 5, I could have multiple in the same state. So let's just put these crosses. Let's put 4 of them to know that these are boxes associated with degeneracies, right? There are 5 degenerate states, 5 of them. I'm just putting this as a placeholder. Now I can put, for example, 2 bosons here, 1 boson here, 3 boson here. How many do I have? 6. 1 here and 0. Good. This is a way of distributing 7 bosons in 5 boxes. Good. So what is the total number of possibilities? Well, the total number of possibilities would be the total arrangements of these crosses and these circles. The number of crosses is dn minus 1. Right? I have 5 boxes, I put only 4 boxes. Right? So what is that? There is nn plus dn minus 1 factorial ways, different ways of arranging these configurations, arranging these. But of course, the swapping the crosses and swapping the bosons won't matter. So what we end up with is nn plus dn minus 1. Choose nn. And then you do this for all states, and you end up with the following bosonic formula. Bosons. Q of n1. This is a problem writing on the board. I run out of time pretty bad. Okay. All right, let me pause for questions. I am not making fun. The point I made so far was that whether your statistics is, this is statistics, right? Whether it's you have bosons, the statistics is different. Whether you have fermions, the statistics is different. If you have distinguishable particles, it's very different, but nobody cares about distinguishable particles. Right? Okay. Now, how much time do I have? Negative 1 minute. Yeah.
Check. You're writing subscript n minus 1, not d subscript
Yes,
n
yes, yes.
minus 1.
D subscript n minus 1. This minus 1. All right. Okay, so let me say it in words where this goes. Do you guys want to see the? Let me say what I was gonna do, and then you tell me what you want to see next time. Maybe I can do it next time as well. What we derived was accounting the number of states with a particular configuration goes on the first, right? The next step is to turn this into something like the Maxwell-Boltzmann distribution, so Dirac-Curve distribution. So, what is the principle over there? There are two things. First is, I forgot to say this. If I have this configuration that I started with, right, there were 13 configurations with these identical particles, right, equal probabilities, remember? There were 6 of them that had to do with this 7, 17, and 5. If you ask the question as what is the most likely state, that would be it. Right? In classical physics, not only we associate, in statistical mechanics, not only we associate equipartition, we often ask another question, which is what is the most likely state? Right? This is in line with that idea of trying to say that okay, so the density matrix, but what if I want to just most likely state? What happens is as the number of particles n, where is it? N particles. When n becomes large, the distinction between those different states become very, very different. There will be state that become so likely that overwhelms everything else. This is an intuition that comes from called law of large numbers. If you have lots of particles, basically, if you did the equipartition, the vast majority of them will have probability 1 over gazillion, and then there will be one state that's almost 1. So we're going to be after that likeliest state. I'm out of time. I'll probably finish this next time because I did a poor job at the end. Are there any questions with the philosophy, right? So the next step is searching for the likeliest state. Let me just write something on the board. Show of hands, Lagrange multiplier methods. How many of you guys know it? All right, I'll have to do that. So I will not write anything on the board. All right, thank you so much.